welcome to RF transceiver design course. In last class, we have stopped at RF testing. We have discussed about the various simulation method and EDA tools, and we have also discussed about the link budget for RF transceiver design. So, in this class, we will discuss one of the important part of RF transceiver design, that is the testing and measurement. So, testing and measurement is one of the separate course at all, but I will just give the brief overview of the testing and measurement of RF components. So, if we consider the RF chip or RF circuits, once you have designed the chip and then you have taped it out with any foundry, then you will get the chip in the either die form or in the package form. So, based on that, there is a three ways you can do the RF testing. So, one of the ways is a directly die test. So, in order to test the die, you need to have a probes. So, there are different kinds of probes are available, that is called ground, source, ground, where there is a 3 pins will be there on the probes, and each pin will have a one pin is a ground, another will be source, means signal, any signal, there is a ground, and again there is a ground. So, in market there are various kind of probes, RF probes are available, and you should purchase one of the probes according to the pitch. So, what is a pitch? The distance between two pads from middle of this pad to middle of this pad, that is, this distance is called a pitch. So, this based on the various pitch dimension, there are probes are available, let us say 100 micron or 150 micron or 60 micron, and it is also as per the design guideline provided by the foundry, because you cannot have very small distance between two pads. So, if you see in this figure, there is a one figure which is shown is a bare die. Now, in that bare die you can see there is a different pads are at different distance has been kept, so that you can do the bond wire, you can do the die testing by using the GSG or various probes. Another method is a bond wire plus PCB. So, in bond wire plus PCB, what is required, because what is happening, that if you are making a complete RF transceiver design along with some back end baseband components ADC or PLL, which required many DC input. So, such as a reference or any other DC input. Now, this DC input, there is a there is a limitation in keeping the number of probes on the probe station. So, when you want to do the measurement, you require a probe station, and that is very difficult if you do not have a probe station, and if you have many pads, there are many pads or let us say many pins if you have, then it is very difficult to put on the difficult to do the RF testing. So, the another method is a bond wire plus PCB. What it means, you can see that there are various pads you can keep, and that will be bond wire directly on the PCB. Instead of the package, it will be directly bond wire on the PCB. Similarly, there is a direct testing of PCB, where you just need a PCB and a package. So, this is a package which is provided by the foundry. There are various kinds of package are available that you can use for RF testing. So, now we will see each of these in detail. So, what are the essentials for die testing? That is listed out here. One of the important thing for die testing, that probes availability as per the layout. As I discussed, if you have a GSG, means if you have a GSG probe available, then as per in your layout you need to have a pads at the defined pitch. Let us say if this is a GSG, then this is a ground, this is a signal, and this is a ground. So, your layout should also reflect the same thing what you are going to test. So, for any RF transceiver design, before going to the layout and sending your chip for the tape out, you should have this in your mind, that how you are going to test your chip. Either you want to go for the package, or you want to go for PCB plus die, or you want to go for only die testing. So, essential for die testing is a probes, availability of probes and what kind of probes you are going to use. Then you also require a multiple equipment. It is essential for not only die testing, it is essential for all the RF testing. Let us say network analyzer, spectrum analyzer, source generator, or signal generator. There are vector signal generator are also available, DC supply meter, various DC source, and noise source for noise figure measurement. So, all this is required before going for the testing. So, you should also have a prior understanding that how you are going to test your chip, and not we should not forget the cables and connectors, because at a high frequency cables and connectors are also important. It adds a loss, and it also degrade our performance. So, we should have a specific RF cables and connectors like SMA connector with various frequency ranges. You also require the balance and combiners. If you have a differential signal, you need a balance, or if you want to combine a two differential signal, you need a combiner. So, that also is a required externally. When you, if you are doing a differential signaling, then there are probes available which are GS, GSG. So, in differential you can give this as a positive signal and this as a negative. So, you can provide a differential signal also, and you can take it out a differential signal. This is called a GS-GSG probe. Even there are SGS probes are available, which is called signal ground signal. So, various probes are available. You can prior to testing, you should know what are the kinds of probes available. Now, when you want to go for bond wire plus PCB, and one more thing, that when you want to do the when you want to do the die testing, you also need to have a probe station. Now, to reduce the parasitics and complexity of probe testing, because probe testing has a limited input output capability because of the probe station limitation in the probe station probes, number of probes. However, that if you have a if you want to reduce the parasitic, because bond wire will add the parasitics, and if we do not want to go for the complexity of probe testing, we can go for this hybrid method. It is a bond wire plus PCB. It will add more parasitic than a die testing, but it will have a less than a package, because package bond wire length is higher compared to the this, and in this you can control the bond wire length as well, or you can also use a bond wire inductance considering the as a inductor in your circuit. So, that you should do the prior calculation, that what is the bond wire inductance and how you will incorporate in your circuit, and that should be the model of the bond wire should be kept in the simulation while you are doing the simulation. This is very easy to handle because once it is a bond wire, there is a globe top will be kept on the die, so it will not change. So, it is very easy to handle compared to the probes. However, the difficulty is in bond wiring. It should be done with a expertise in bond wiring. So, otherwise what will happen, that one pad will be touched to other pad, and it should require the either mechanical bond wiring or robotic bond wiring, or with expertise it should be done. What is the requirement for bond wiring? You should know the pitch should be known prior. What is the minimum pad area to the bond wire, and pad metal used? Because what will happen, that if your pad metal and your bond wire metal is different, or it does not stuck to the your actual pad, then there is no contact will happen. So, that also you should know prior, that what should be your bond wire metal and what is your pad metal. Accordingly, you can design your PCB as well as you can go for the bond wiring. So, equipment are same, but this is the additional thing you required for a bond wire plus PCB testing. Now, we go for a package. Now, we will discuss about the package testing. So, package testing, you should know the bond wire diagram should be clear, because let us say when you have sent your die for fabrication, you have a multiple pads on your chip. Now, these all pads that you have kept on chip, and you need to provide a bond wire diagram to the packaging company who is going to make a package for you, and that bond wire will tell that which pad is connected to which pin number. So, if this is a pin number 1, this is a pin number 2. So, this detailed bond wire diagram you should provide to the packaging company, and they will ask you this, that how your connection will be made prior to getting the package. So, you should have a clear understanding that what is your bond wire diagram, which pad is connected to which pin. Then for RF testing, standard packages that add very fewer parasitics have been used, such as QFN or BGA, etc. So, there is a different kind of packagings. Let us say QFP packaging are least used because it add more parasitics. That is why we need to use a package that will add a less parasitics, such as QFN or BGA. You need to also use a matching network should be inside the chip. So, when you are doing the package testing, your matching network should be inside the chip, so that challenge is it will have a low Q and low lossy, it is a lossy. So, in that case what will happen, that if your matching network is not inside the chip, this package will also add the inductance and it will detune. Even it is put on the if you have put the matching network also on chip, you need to properly model this bond wire and you need to keep while doing the simulation, otherwise your result will change. External matching is one of the concern, because you need to model the S parameter and design PCB while considering the matching issue. It is possible, but you need to priorly taken care of how you are going to do the matching. With L and C, only narrowband matching is possible. For wideband matching, it will take more space and be lossy. So, that is also one of the challenge. And for RF input signal, use the RF transformer concept. for impedance matching. Your PCB design should be tested in any EM software. So, what will happen that your PCB trace, as when we have discussed the transmission line, at that time I discussed if your transmission line at high frequency, even when you are tracing out on the PCB, it will be act as a transmission line. So, that will change your impedance matching. So, your PCB should also be tested prior on the EM software. So, these are the three ways that we can do the testing in RF transceiver chip. Now, we will summarize the challenge. What are the challenge in the RF testing? RF devices need extra attention during testing. That is one of the biggest challenge, because it is not a DC testing. Its frequency is not around 100 megahertz or 200 megahertz. It is very high frequency. So, impedance matching at input and output ports to ensure that optimal power transfer will happen. So, that is always needs to be done. If you have not done proper input and output matching, your circuit will might not give you the response, or your result will be deviated from whatever you have simulated. Another challenge is a shielding from external wireless signal during testing. So, what is happening that around us there are many wireless signals, and there is a possibility that some of the antenna effect will come into the picture while in the PCB or while doing testing, and you might see the signal which exactly which is not existing and which you do not want. So, while testing you should have proper shielding. In antenna or other component testing, there is a anechoic chamber has been used. So, if you are working at very high frequency and if you want to avoid the unnecessary external wireless signal, you can put you can test your chip in the environment like a anechoic chamber. The test needs to perform all of the above with, you need to also have a challenge in terms of getting a cheaper instrumentation, which is one of the big challenge. You will not get very low cost commercial tester if you go for higher and higher frequency. So, that is another challenge. You required a very high quality equipment and which is a costly. You need to perform a test in a short duration. If you that is a challenge, because this testing require a longer duration. It might take 1 or 2 months or 3 months to rectify some of the problem if you face. So, doing a testing in short duration is also one of the challenge when you are designing a RF transceiver chips, and achieving a high degree of accuracy in testing is also one of the challenge. You need to ensure that you have a good accuracy while doing the calibration and finding out the losses of each cables, components, and designing the PCB planning. So, planning of the RF testing is important. That is why this lecture will help you to do the planning for your chip testing. I will just give from one of our publication. This is one of the fabricated die of the RF mixer, and it is a probed on this is a probe testing setup. You can see that this is a GSC probe, ground signal ground, and this is a GSGSG probe. This is a differential probe. This is a inductor, this is a capacitor LC matching, there are active circuits, and the output is also GSG. So, this is one of the side is RF input, LO input, IF output, and VDD and ground. So, while if you want to do the die testing, you also need to ensure that all the bias that is required for your circuit is generated inside the chip. If you have a more bias pads or pins, then it is very difficult to do the die testing. You need to go for the PCB plus probe testing. So, this is one of the setup, basic setup of the, you require a probe station. These are the various RF source, balloon, spectrum analyzer, power supply, design coupler. So, all this you required when you do the probe or die testing. So, this is a network analyzer, one of the output of the network analyzer. I want to show you that this circuit was designed at 2.4 gigahertz, and you need to have the input matching, that is at 2.4 gigahertz. So, you need to measure the S11. So, when you measure the S11, this is how the S11 will look on the instrument. This is a Agilent technology. Now it is called a Keysight. The input is matched at 2.4 gigahertz, and you will get the S11 less than minus 10 dB. So, you should have a minimum reflection at your desired frequency and maximum transmission. Another is RF to LO, means if you are designing a mixer, we already discussed the isolation. If you want to find out the RF to LO isolation, you can see that it is a more than 56 dB. If you want to test the PCB, this is a PCB setup for measurement. So, there are connectors. So, as I told, you need to have understanding of connectors. Then this is a what are the power supply, how you will connect the power supply. Then balun, if you have kept on chip or off chip you require a balun, and you need to have a signal generator for LO frequency, for RF frequency you require a spectrum or network analyzer. Same setup has been shown here. So, these are some of the external balloons shown in the figure. Now, when you do the when you measure the gain of fault end mixer, means this is a fault end mixer that I will also provide you the reference, you can go through more in detail. So, here this is a RF input. When you give RF input of minus 33 dBm, when you consider the connector cable and bias T other losses, your LO input is 1.5 dBm. So, you can see that there is a LO is also there, IF is also there, minus 30.66 dBm IF output, that is around here. So, IF is at around 100 megahertz, and there is a 100 megahertz difference between RF and LO frequency, and your conversion gain can be calculated. What is the conversion gain? You can revise, it is IF by RF. So, in dB it is IF minus RF. So, minus 33 you will get your minus 33 is the input, minus 30 is the output. So, you can get minus 30 minus 30.66 plus 33, you will get this output. So, this is how you should do the measurement of the gain. There is, you can also use a network analyzer to find the gain. You can also use a spectrum analyzer to find the noise figure. We all know that noise figure is nothing but SNR in by SNR out. You can find the SNR in by finding this average of this average of the noise floor minus the signal amplitude. You will get the SNR in, means your input signal SNR. You need to make sure that your resolution bandwidth and video bandwidth is equal, or there is another rule of thumb that your resolution bandwidth by video bandwidth. When we discuss the noise figure, at that time also I mentioned that RBW by video bandwidth should be around 0.3. It is not a standard, but it is based on the design experiment that can be analyzed. So, what it says that always your video bandwidth should be little higher compared to the resolution bandwidth. So, you then you find the SNR out, your noise figure is nothing but SNR in minus SNR out, you will get around 60.93 minus 50.79, around 10.14 dB. That is the noise figure of the mixer. There is another method also, that is called a Y factor method, and in that you need a noise source. So, that also we have discussed when we have discussed the noise figure. So, what you need is a setting, you need to do the frequency setting, you need to have ENR table setting. So, it is a excess noise ratio setting, excess noise ratio, which is provided by the noise source company, which is tested for a different uh, noise source when noise source is on. So, what is excess noise ratio in dB? When noise source is on and when noise source is off. So, that difference will give the excess noise ratio, and it is provided at different frequency, and that you can test. You need to have a calibration. So, you need to do the calibration. This is how you can do the cabling for device under test. This is your RF input, this is a IF output, this is your LO input. You have a spectrum analyzer and noise source which is connected. So, this noise source output with a BNC cable, the means noise source control. So, in the spectrum analyzer there is a noise source control which control the noise source which is connected by BNC cable, and that will be the input to the your device under test. And you also have a LO, local oscillator signal, will be applied to the DUT, which is connected with USB GPIB cable. Because you need to also control the LO frequency according to the whatever inputs you have given at the spectrum analyzer. Then measurement of the total noise figure DUT plus measurement system using Y factor method, and it calculate the noise figure of the DOT, that is a noise figure underscore 1. So, you need a Y which is internally calculated because ENR is provided, and the finally noise figure is given by excess noise ratio by Y minus 1. We already have discussed this during the noise figure measurement. So, I am not going into the detail, you can go back and listen that lecture. Then another is a linearity measurement. So, we already have discussed the IIP3. If you want to test the IIP3, you need to provide a two tone. So, that two tone, when you provide an input, so you need a two signal generator or a generator which provide a two tone. So, that two tone you supply to the your circuit, and then there is a third order component will be available. That third order component is providing you the IIP3. So, the difference between these two will provide you the delta. So, your IIP3 is equal to P in delta by P in plus delta by 2. So, this we already have discussed when we have discussed the IIP3. So, in this case IIP3 is around minus 1.5 dBm. If you are interested to go for more in detail about the result and discussion on the chip that we have fabricated, you can go through this reference. All the details has been provided in this reference. So, this is how we in this lecture I just want to give you the feel that how the testing has been happened for this kind of RF transceiver chip, and one of the important component in RF transceiver design is a mixer which down converts the signal. And in this lecture we have seen that how various parameters like IIP3, noise figure, then gain, conversion gain, isolation, input matching, all that has been measured. So, this is about the RF testing. So, now if I summarize the entire course, We have started from the basic understanding of the individual parameters, then we have moved to the each and every components in detail. We also have discussed the RF transceiver architecture, we discussed the impedance matching methodologies, all the passive components, active components. So, all the lectures has given a deep understanding, and if you are interested to go more in deep for individual component also, you can go through the each lectures. So, this course will help you to design RF transceiver for any application. It can be sub 6 gigahertz, it can be millimeter wave, or it can be sub terahertz, or even at terahertz. So, all the features has been discussed, even some of the basic understanding of PLL, power amplifier, synthesizer, and basic of oscillator has been discussed. If you are interested more in go into the deep on each of their subject, there are a separate course available that you can go through it. I hope this course has given you in depth understanding, and you will find this entire course to be useful in your RF transceiver design, and you can go back and study each lecture when it is required. Thank you all of you for attending this course. Thank you.